I would like to add some remark. Given a critical point, that means that the first derivative turns 0 at this point, and for example, the second order derivative is negative, we can say more. Then x star is a strict local max. That means that in some neighborhood or interval, if we withdraw this point, then on this interval the following inequality holds. It's strict. Analogously, if at a critical point the second order derivative is positive, this point is a strict local minimum. Now we proceed with the descriptions of local and global extrema in case of the function of many variables. And let's suppose we have a function. This time this function depends on n variables, and it's defined, let it be defined on some set U, open set, in Rn. For our purposes, it's quite sufficient to consider a function of two variables. Okay, and we start with drawings, with the graphs of these functions. So let's suppose there is a function x squared plus y squared, where the point xy belongs to R2 space. How the graph of this function looks like. This time we have to draw a graph in 3D. That's how we get three axes. So it's easy to draw the graph. It looks like a bowl. We can say this is a bowl-shaped graph. Looks like that. Well, clearly the origin is the minimum point of this function, and actually it's a global minimum, because if xy is not taken at the origin, then x squared plus y squared is strictly greater than 0. So actually we can even make the same remark that the origin for this function is the point of the global strict minimum. Now, if we reverse the signs in the definition of the function z, and we'll make it minus x squared minus y squared, we have to reflect this bowl upside down, and the graph this time looks like that. It looks like that. And the origin this time becomes the point of the strict global maximum. What if we take plus in front of x squared term and subtract y squared? It's interesting that the surface, which is a graph of this function, is not that easy to draw compared to these bowl-shaped surfaces. So in order to draw the graph for this function, let's cut this surface by the coordinate plane. Let's consider that y equals 0. Then this term turns 0, and all we have to do, we have to draw the parabola which faces upward. But if we start cutting this surface with the vertical planes, which passes through any point on x-axis, then we get a collection of parabolas which face down, and that's how the surface looks like. And it looks like a saddle. So you can sit there at the origin and stretch your legs down. That's why the point, which is the origin, is called a saddle point. Now it's time to proceed with the formal definitions of maximum and minimum. So, let's suppose our function is defined as earlier on U, which is an open set in Rn, and we say, so that will be definition. Now we're defining global maximum. The point x star, well, clearly this is a vector, but I won't indicate this because it will be self-evident, is the global max if for all x from U the following inequality holds. What about the local maximum? A point can be considered as a local maximum of such a function if there exists, so we have finished with that, and now we proceed with the local maximum. So what we need to add to this, to the previous definition? If there exists a ball about the point such that f of x is no greater than f of x star for all x we intersect with the U set, then we call such a point star is a local max.